Hello dear students, welcome to physics class. Today in this video lecture, we are going to discuss the electric field line, the properties of electric field line and the pattern of the electric field line. So let's start with the pictorial representation of electric field. In the first diagram, you can see we have a positive Q charge and we know the electric field lines for positive charge we will draw outward side. So in this way we can draw the electric field line. But if you see the diagram carefully, there are three vectors. First vector, this is first, second and third vector. If you compare the length of all the three vectors, you will see the first vector is larger than the second one and the second one is larger than the third one. So larger vector represent the strong electric field. What do you mean by this larger vector? It represents strong field. So larger vector we will represent near the positive Q charge. We can take this idea from this formula. E is inversely proportional to r square. As distance is going to increase, the field is going to weak. So we can represent the weak field with the shorter vector and the large field with the strong field with the larger vector. So this first one near this vector till here the field is strong. From here to here the field is going to weak and here the field is also going to weak. So as you are near to the charge, the field will be strong, and if you are going away from the charge, so field will decrease. Similar way we can represent for negative Q charge. So as we know, for the negative Q charge, the direction of electric field lines we will represent towards the charge. For positive charge outward side and for the negative charge inward side. So now you can see here again, near the charge the vector length is long. As you moving from as you going away from the negative Q charge, the length of the vector is going to short. So shorter length mean weak field and the larger length of vector means strong field. So in this way you can represent the electric field lines. This is a pictorial representation. To represent these lines in an easier way, you can even draw the electric field lines in this way. So you can draw a continuous field line. Simply charge is there and you can draw the vectors outward side for positive Q charge. So let's see here again. So the first diagram, these two diagrams are almost similar to this and this. This is your first diagram. You can see here the Q is greater than 0. So what does it mean? Q greater than 0 means your charge is positive Q. Okay, so in your exam they can give you draw the field lines for Q is greater than 0. So in that case you will draw this kind of line, and if Q is positive, then still you will draw this kind of line, this kind of diagram. And what about the Q is less than 0? So Q is less than 0 means your charge is negative. So for negative charge the arrow will towards the negative charge. So in that way you can represent the electric field lines strength. This is the electric field line strength, because the larger the vector the stronger the field. So you can read the A point, representation of electric field in terms of field vector. These representation in terms of field vector. And the size of the arrow. The size of the arrow will give you the strength of electric field. So these 2 points are important. And if you want to represent electric field lines in an easy way, so even you can represent electric field line in this way, but these vector does not represent the strength. If in exam the question is draw the electric field lines with the strength, so in that case you will draw this kind of picture. Next, when you have the one is positive charge, another one is the negative charge. When you have two unlike charges, so how will you represent the electric field line? So we will draw the electric field lines for positive and the negative charge. If you have one positive charge and another one is negative charge, negative Q charge, so how will you represent? We know for positive charge the direction of electric field lines towards outward side, and the electric field lines are coming outward side. This line is also want to go this side, but here the negative charge is here, so this line will feel attraction toward negative charge, and it will move towards the negative charge. Similarly, one line is coming out from here, and this line will also feel attraction towards negative charge. So in that way it will contract towards the negative Q charge. Similarly, you can draw number of field lines. So in that way you will get this kind of pattern. And we know for negative charge, electric field lines are going inside the negative Q charge. So for negative Q charge, you will represent electric field lines like that. So this is the way to draw the diagram. You can see this diagram. This is the exact diagram for positive and negative Q charge. And here the P point, at P point you will see one tangent is there. So if you want to find the direction of electric field line at a particular point, suppose we want to find the electric field direction at this point, so what we will do? You will draw a tangent. This tangent will give the direction of electric field line. Okay, so this is the positive and negative charge interaction. Now the second diagram is when you have a like charges, both are same kind of charges. Suppose now we have positive Q and positive Q charge, same kind of charge. So what will happen? Because this is negative charge, then for the negative charge the arrow will be outward side. And what about this? Again the arrow will be outward side for positive Q charge. Now what will happen? Because from here the electric field line is coming outward, but here already positive Q charge is there, and we know positive will repel. So this line will feel repulsion due to this one. So this one also feeling the repulsion. So these will start repelling, and that way. So this is repulsion. Each line is feeling a repulsion from the near one charge. Similarly from here, all these are feeling repulsion. So in that way you can represent the electric field line, pictorial representation of electric field line. So in that way you can draw the diagram, and you can see the previous diagram. This is the correct representation of electric field lines. Now you can see there is one word, the name is attraction. Electric lines of force contract lengthwise to represent attraction between two unlike charge. So here is a contraction is there. These field lines get contract. This field line is going away, but due to this negative charge it feels attraction and it get contract. Otherwise if there is no negative charge, so it will go straight. It will not feel any contraction. But because here the negative charge is there, so it is feeling a attraction toward this and it get contracted. This is the case of unlike charge. And in this case there is a word exert lateral pressure. Sideways lateral pressure is there. This lateral, you can see if the positive Q charge is not there, so this line should be go like that. But here positive Q charge is there and this positive Q charge is repelling it. So this ray feel a repulsion and it get repelled. And we can say there is a lateral pressure exerting on these rays. Loop. They will not return back from they are emitting from the positive charge and again they are coming back to the positive charge. This kind of loop they will not form. These field lines always start from the positive charge and end into the negative charge. Now the next point, the tangent to an electric field line at any point give the direction of electric field at that point. So now if we want to find, this is a electric field line, yellow color is electric field line, and we want to find the direction of electric field at P point. So we will draw a tangent. The tangent will give the direction of electric field line. Next, two electric line of force can never cross each other. So if we have two field lines which are crossing each other, so what does it mean? If two field lines are crossing each other, so you can draw two tangent on that, and you are drawing a two tangent at a single point and it is indicating two direction. Two direction at a point is not possible. So that's why two field lines cannot intersect each other. Okay, so two field lines at a point is not possible. Next we will discuss the sixth property. The electric line of force are closer where the electric field is stronger, and the line spread out where the electric field is weaker. So in the first diagram you can see here, if you count the field lines, these are more as compared to this one. So Q is greater than this one. So where the field lines are more, it means electric field is strong. More the crowd of the electric field lines, more the strong the field. So here field of this first one will be greater than the second one charge. Next line. The electric line of force are always perpendicular to the surface of positive and the negative charge. If you have a plain slab and you want to represent the electric field line, so you will represent in that way. This is the first diagram. If you any infinite plane sheet, infinite rod, or a simple rod, so in that case you will draw electric field lines on the both directions. Let us consider we have one sheet and we want to represent the electric field line. So how will you represent? On both sides. Uniform electric field, we will represent both sides. You can see the previous diagram in that way. Now next is, if any arbitrary surface is there, so again on that surface electric field lines are always perpendicular. This is also the properties of electric field line. Next one is, electric line of force contract lengthwise to represent attraction between two unlike charges. So you can see the previous diagram. Here two unlike charges are there, so there is a contraction between two unlike charge. So this is our eighth property. When two unlike charges are there, contraction will occur. And now the next one, here two positive charges there, two similar charges are there. So for similar charge, what will happen? Lateral pressure will exert because both are repelling to each other. Now we will go to the next property. The next property is property number 10. The number of field lines per unit area cross-sectional perpendicular to the field line is directly proportional. Suppose you have an area and the number of field line crossing this area, the number of field line, suppose you have n number of field lines and A is area of this surface. So number of field line crossing this area will depend on the intensity of electric field. It will depend on the intensity of electric field in that region. So number of field lines crossing per unit area will depend on the electric field intensity. How many number of field lines are coming inside that area. Now the next property is, electric field line does not pass through a conductor. If you have a conductor, so inside that conductor there is no field. If you have a conductor, there is no field line in that conductor. So we will understand this concept. Let us consider this is external electric field and we will place a charged, not charged, we will place a conducting slab between this positive and negative charge. So what will happen? This is conductor. This is our conductor. Here we will understand why the field line inside a conductor is 0. So we know induction process, when we placed a conductor near the positive charge, so what will happen? Induction will occur. So due to that, here negative charge will appear and here positive charge will induce. So now inside the conductor, what will happen? A field will generate and that field is known as polarized field or internal field, we can say. So let us consider the field is EP, polarized field, and due to this positive and negative charge, there is one field that is known as external field. So as here the positive charge is there, all the electron will start moving toward this side, and because of that positive and the negative charge, a field will develop, that is your EP field. So how long this field will be there? As all the electron will move from this side to this side, till now that field will continues, EP will continues. Initially EP is small, but as the electrons are moving from this portion to this side, this field is going to increase, and one time will come when the internal EP field becomes equal to the external field. So that time the both field becomes equal and the net field become 0. So that's why inside a conductor electric field is always 0. Okay, so that is the reason inside conductor electric field is 0, and that is also known as shielding effect. There is no field inside the conductor, and that is known as electrostatic shielding. Next topic is electric line of force can pass through an insulator. Yes, electric field lines can pass through an insulator. When you place the electric field line, this is your field, suppose positive and negative charge is there, and you place the device insulator. So what will happen? Due to this field lines, all the negative charge will start moving toward this side. Okay, so net field will not be 0. Some field will be developed due to this small negative and positive charge. So internal field will develop here also. This is your external field, this one is internal field. So yes, inside the insulator electric field lines are there. So these are the properties of electric field line. We will do one numerical problem based on the electric field line. Let us consider we have Q1 charge. We have to find ratio of Q1 and Q1 charge. Find Q1 by Q2. So now you can see here this is positive Q1 charge and 5, 6. These are the field lines, and these field lines are going inside this Q2 charge. We have Q2 charge also. So these field lines are entering in the Q2 charge. Okay, and here also some field lines are there. This is negative Q charge. Because these field lines are entering, it means this one is Q, 2 is negative. So now we have to find the ratio of Q1 by Q2. So how will you find the ratio of Q1 and Q2? So count the number of field line which is entering from Q1. So your Q1, count the number of field lines which is entering inside the, which are exiting the Q1 charge. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it means Q1 is 11. And in this case, how many field lines are coming inside? This is 1, 2, 3, 4, 5 and 6. So inside Q2 charge, 6 field lines are coming. So Q2 will be 6. And ratio will be Q1 by Q2. That is equal to 11 by 6. So in that way you can find the ratio of charge by counting the number of field lines emerging and going inside a charge. So that's enough for today. Thank you, students.